Over the past 9 months, this design team has taken on the task of designing and manufacturing a biomechanical exoskeleton for Dr. Yusuf to use in his lab. The objective of this project was to develop a multi-degree of freedom research platform of an exoskeleton system, which will allow future research of the experimental mechanics laboratory. We were expected to design, manufacture, and test an exoskeleton system to demonstrate its functionality and technical flexibility for future biomechanics-based research. Dr. Yusuf gave us a budget of $500, and because a device like this had never really been built before, we had a lot of research and planning to do. We came up with a few designs involving soft polymers and elastic before settling on a design that mimics the biology of the actual spine. The final design alternates hard plastic vertebrae with flexible silicone discs. As far as the electronics are concerned, we decided a design using bend sensors and potentiometers would be best for our timeline and budget. There are 7 requirements for this system. Requirement 1. The device must collect data from a majority of the spine. To fulfill this, we decided our device will extend from vertebra C1 below the skull to L5, directly above the hips. Requirement 2. Design of the exoskeleton shall allow for acceptable portability and accessibility. This requirement is very broad and includes needing the exoskeleton to fit 90% of college males, take less than an hour to set up, and weigh less than 25 kilograms. In order to make the exoskeleton fit our target population, almost every part of it is adjustable. 19 of the 26 vertebrae can change height using a pin system, and each strap is adjustable in at least one spot. Once the exoskeleton's height is adjusted, it will take almost no time to set up, as it just needs to be put on and buckled. Because the entire system is mainly made of plastic and silicone, the weight limit was easily attainable. Requirement 3. The exoskeleton shall collect data and output it in a sensible format. Because the bend sensors do not directly output information on the forces of the spine, an Arduino had to be incorporated with code to convert the bending data to a force. Requirement 4. The exoskeleton has to output values that make sense. Dr. Yusuf informed us that our device should output numbers within 10% of what is found in literature. Requirement 5. The exoskeleton shall not hinder the nominal ranges of motion for human movement. In order to satisfy this requirement, we had to ensure that each portion of the spine was able to move in the same ranges of motion as the normal spine. This ended up being between 10 and 30 degrees of flexion. For rotation, the lower spine needed about 10 degrees and the neck required up to 45. After many iterations of silicone disc design and ratio, we decided on a donut-like shape that did not reach the edge of the vertebrae on either side with a 2-to-1 ratio of silicone. Requirement 6. The exoskeleton shall output to a single source for ease of use. We decided on an Arduino Mega to fulfill this requirement. While the device is in use, 10 sensors at a time can be connected to the Arduino and transmitting information. There are 5 bend sensors that can be placed anywhere in the exoskeleton, and the potentiometers can be chosen by switching out the Molex connectors in the electrical box. Requirement 7. The exoskeleton shall operate on a power source that does not compromise the integrity of the internal electronics and be able to run for at least 1 hour without being connected to a power supply. A 5-volt battery is plenty of power for both of these. Manufacturing this project ended up being more work than we were anticipating. Each section of the manufacturing involved very different processes. The 19 vertebrae that changed height needed to be printed in 2 halves, and the remaining 7 cervical vertebrae were printed as 1 unit. The prints ran for a total of about 40 hours. Each disc was casted using an elliptical donut-shaped mold so that the potentiometers could be placed in the center of the discs. We used UMU 30 silicone at a ratio of 1 part A to 2 parts B to achieve the desired flexibility in each disc. After curing for 6 hours, the discs were complete. The bend sensors are not permanently attached to the exoskeleton, so their assembly simply involves soldering the wires to the sensor, applying the heat shrink, cutting the wire to length, and crimping the end to the Molex sleeve. The potentiometers are a little more complicated because they need to be surrounded by the silicon discs. Before gluing each disc in place, the potentiometer needs to be positioned in its hole in the vertebra and have the appropriate length rubber hose secured on so it can sense the rotation of the vertebra above it. Then, the disc can be glued on its surrounding vertebrae, and after drying for 24 hours, it is ready to go. In order to read the values given by the sensors, we wrote a code that plots the time in seconds against the position of the sensor while transferring all this data to an SD card. The SD card then outputs all the data to an Excel sheet. From the Excel sheet, we can use formulas to convert the position to the appropriate force. In order to attach the exoskeleton to the body, a strapping system using cotton and elastic was designed. The elastic keeps the exoskeleton pressed against the body, while the cotton pulls the exoskeleton as the body moves. After the entire exoskeleton was assembled, individual straps were cut to length and sewed into place. There are buckles attached to each strap on the front of the body so large adjustments can be made, and each cotton strap has a strip of Velcro so that finer adjustments can be made for a snug fit on each person. After almost 9 months of work, we have a fully functioning biomechanical exoskeleton that can sense flexion and rotation along the length of the entire spine.